Hello everyone. We were discussing about network layer protocols. In that, we are learning about IPv4 datagram packet. So this is the IPv4 datagram. So we'll see one by one now. The first field is VER, which stands for version number. So VER is of 4 bits, that is version. So this is the field which indicates the version of IP. So in this case it is IPv4. So the version is 4, so the value in place of VR is 0100. So that is in binary number. So 4 is represented by 0100. So that field version will be always 0100 in this case. Next is HLEN. Once again, this is 4-bit space. So HLEN stands for header length. 4-bit data. So this is a 4-bit data which defines the length of the datagram header. So the length of this datagram header is defined by or represented in this particular field. As we know, the length of the header is variable. It is from 20 to 60 bytes. So when the device or the destination receives the datagram, it should know where exactly the header stops and where exactly the data which is encapsulated is going to start. So this is the one which is going to help the receiver in checking or identifying where exactly the header stops and data where it begins. So the total length of the header is calculated as 4 byte word, and then it is divided by 4, and whatever the result we get, that value will be inserted in this field. I repeat, what is the total field or the total length of the header is there, that is calculated as 4 byte words, that actually the 4 byte word. So this will be divided by 4 so that it is fitting, it can be fitting that HLEN 4 bit. At the receiver, who is going to receive the data, and it is going to multiply back with 4 to find the total length. So at the sender, it is divisible, it will be divided by 4, and that value will be inserted here and it will be sent. At the receiver, this data will be taken, multiplied by 4 to calculate the total length. The next field is service type. So it is of 8-bit, and this particular field is going to define the type of service provided by the protocol. So however, we'll see this in the next coming session. Just remember that this is the 8-bit which is going to define the type of services provided. Next one is the total length, which is of 16-bit. So this 16-bit field gives the total length of the IP datagram in bytes. That is, it includes header as well as data. So total length of the IP datagram will be represented in the total length field. Usually the size of the datagram is less than this. That is, whatever is specified here, compared to that, the length will be very, or it will be less than whatever is specified in this case. And this field helps in identifying which packet has arrived completely. So to find the length of the data coming from upper layer, subtract that, subtract the header length from the total length. So we are going to get the length of the data coming from the upper layer. So the equation is, if you want to find out the length of the data, then take the total length specified here, subtract the header length, that is H HLEN data multiplied by 4. So total length minus HLEN into 4 is going to give us the total length of the data what network layer has received from the transport layer. So as we know, the header will be added in this particular field. So one might think why this field is uh, required. So why this field is required? That is total length field is required here. When the frame arrives at the destination, the header will be removed and only whatever the data is there, payload is there, that will be retrieved. So there might be cases along with the datagram, that is along with the data of the packet, few might include the padding data too, because there is a criteria for minimum size of a datagram. When that is not met, that minimum criteria, then there is a procedure called padding to meet the minimum size criteria. So that padding will be added and then it will be encapsulated and the data will be sent at the receiver. Once the data is received, so it is going to decapsulate the data and it is going to check what is the actual length of the data. In that, what is the actual data and how much is a padding. So based on the field total length as well as header length, it is going to, that is the receiver is going to identify what is the header length, what is the data, in that what is the actual data and what is the padding data. So using this two field, it is going to identify. Then the next three fields, that is identification, that is of 16-bit, flags 3 bits, as well as fragmentation offset, that is of 13 bits. So total 16 plus 3 plus 13 bits. So these three fields are related to fragmentation. So that is, we have learnt in previous video that whenever the packet arrives from the transport layer, if the data is too large to handle or if it is larger than the underlying network can carry, that is the data link layer can carry, then the packet will be fragmented, that is it made into different pieces, then it will be sent. So these three fields are used to identify, or these three fields are related to the fragmentation. So once again, this is covered in the next coming topic in detail. The next field is of time to leave, that is of 8 bit. What is this time to leave? Whenever a datagram is transmitted or sent, due to some problem or some malfunctioning of a routing protocol, the datagram may be circulated in the internet without reaching the destination. So we have learned something called looping problem when we are discussing in module number 3. The same way, if the packet don't get the particular destination, so the packet might be in the internet only. So this is going to result in additional traffic in the network, right? So simply it will be moving from one place to another without reaching the destination. So this add-ons to the traffic in the network. So this field, the time to leave field, is used for this particular purpose. So what it is going to do is, so in this particular field, uh, the sender is going to specify the maximum number of router a datagram can visit. So in between the sender to a receiver, so how many number of routers, or the maximum number of routers of datagram can travel, will be mentioned in this particular field. So when the source send the datagram, it is going to store a number in this particular field, that is time to leave field. So usually this value will be approximately 2 times the maximum number of routers between the source and the destination. That is, if there are 3 routers, then the value will be 6. So based on the number of routers multiplied by 2, so that is going to decide the value of time to leave. So when every time this packet come across a router, or router processes this datagram, then it is going to decrement this content by 1. So for example, if I keep 6, so once it crosses the first router, then it will become 5. When it crosses the next, it will become 4. So each time when it crosses a router, so the value is going to decrement by 1. So once this value becomes 0, so as it move on, so once the value becomes 0, then the router discard the datagram. So once the value becomes 0 and still it moves to the next router, then that particular router, looking at this time to leave value, if it is 0, it is going to simply discard that particular datagram. Now the next field is protocol. So we know each layer will have different protocols to work on. So the protocol field here is of 8-bit. A datagram can carry a packet belong to any transport layer protocol such as UDP and TCP. So along with whatever the data it receives from the transport layer, all those packets related to TCP or UDP, the uh, the network layer is going to carry. So even datagram can also carry a packet from other protocol. So even it can carry the packet of different protocols that is using the service of an IP. So whichever the protocol using this particular IP, the data related to all those protocols, uh, the datagram will be sent over this IP. So such as routing and or the auxiliary protocols. Uh, the internet usually, or the internet authority usually gives a unique ID which is of 8-bit to a protocol. So what are the different protocol is there in transport layer? So for all of this, there is a 8-bit number or 8-bit unique ID, and that uses, or that will be made available to represent this particular field. So that whatever the unique ID is given by internet authority, so that ID will be inserted in this protocol field. That is, when the payload is encapsulated in a datagram, then the corresponding protocol ID will be inserted in this particular field. And when it receives at the destination, the value at this field will be helping the receiver to know for which payload has arrived, or the protocol of which payload has been arrived. So based on the identifying the protocol ID, the receiver will come to know the payload of which particular protocol has arrived. So there are some protocol and the corresponding values given by the internet protocol or internet authority are, as I said, there are one protocol called IGMP, right? So for that particular IGMP protocol, the ID given is 01. So it has to be represented as 00000001. So whenever IGMP protocol is used. Second one is TCP. So when it is TCP, the ID is 06. That is 00000110. So whenever it uses a protocol related to TCP, then it has to use the ID 06. Similarly, there is something called ICMP corresponding ID is 02, that is 00000010. Similarly, for UDP, the ID given is 17. So whenever a datagram related to UDP is used, then the protocol field will have a ID 17, that is 00010110. Sorry, 0001 and 0111, that is 17. And similarly, there is one protocol which is called as OSPF. When this protocol is, or the datagram corresponding to this protocol is used, then the ID corresponding to this is 89, that is 10001001. So these are the few protocols and the corresponding IDs given by Internet Authority. The next field is header checksum, which is of 16-bit length. As I said, IP is not a reliable protocol. So it is not going to check whether the data carried is corrupted during transmission. So it might have corrupted while transferring from source to the destination. So the corresponding protocol, so the protocol whichever has been used, so only that particular protocol has to take care of error checking. So IP is not responsible for identifying or checking the error. For example, if the destination IP address is corrupted, for example, whatever the destination address has been given, if it is corrupted, then instead of delivering the packet to the correct destination, it might be delivered to the wrong destination. Or is the packet related to fragmentation are corrupted, so the at the receiver datagram cannot be reassembled correctly, right? So since it is a connection less protocol, so packet arrives at different instant of time and it will be out of order. So if that data is only corrupted, then it is difficult to identify which has come first, which has come last, and how to reassemble it. So to avoid these kind of problem, the IP is going to add a header checksum to find with to check with the header error in the header. So this is done by the IP to check whether there is an error in the transmission. The next field is source IP address, which is of 32-bit. So this is the address of the source wherein the data has originated. So the address of the source will be represented in this field and address will be of 32-bit. So we have seen the IP address format in the previous module. So that 32-bit address will be specified in this source address. Similarly, the next one is destination address. So this will be the address of the destination. So either this will be known by the protocol that uses the service of an IP, or it will be provided by DNS. So that particular 32-bit address will be specified in this field. And the last field is options plus padding, which is of 0 to 40 byte. So datagram header can have up to 40 byte as a optional field, and this field is used for network testing and debugging. So whenever the testing of the network has to be done and some debugging has to take place, then this field will be used and data will be entered in this particular field. So that all this is about the header. So whatever we saw this header, in this particular header we'll have all this data from version, header length, service type, total length, identification, flags, fragment offset, time to leave, protocol, header checksum. source IP address, destination IP address, and optional padding. All this data will be embedded in this header file. And as I said, the next part is the payload. So payload is a packet which is coming from the other protocol that use the service of a IP. So this is received from the upper layer, and that will be encapsulated at this network layer along with the header, and then the data will be forwarded to the destination. Hope you're clear with this IPv4 datagram. Examination point of view, very important topic. Usually, this question will be asked. Explain IPv4 datagram. So you need to draw this diagram, and you need to explain this each of this field with 2 to 3 sentences. So with this, we'll see some problems related to this. Yeah, the first example, the question says an IPv4 packet has arrived with the first 8 bit as shown. So the bits are 01000010. The receiver discards the packet. Why? So in this problem, 8-bit data has been given. So and the question is, the receiver has discarded the packet, and we need to give the reason why. The solution. So before going to the solution, as per the problem, the first 8 bits have been given. So if you just remember, in the first 8 bit, the first 4 bit, that is 0100, is going to indicate the version. As I said, it is IPv4, so version 4. So 0100 is equal to 4, so that is correct. Next 4 bit 0010 indicates the header length, so that is header length. Now we have to multiply it by 4. So 0010 is 2. So in order to get the header length, as I said, we have to multiply it by 4. So 2 into 4, that is equal to 8. But as per the requirement, the length of the header should be, the minimum length of the header should be 20. Here it is less than that. So it is only 8. So that is the error. So in this particular problem, header length is only of 8 byte. So you can see the header length is minimum is 20, maximum is 60. But according to the problem, we are getting only 8 bytes. So that is the error. Second question. In an IPv4 packet, the value of HLEN is 1000. How many bytes of options are being carried by this packet? So the header length has been given as 1000, so which is 8. So we need to calculate how many bytes of options are being carried by this particular packet. So as I said, header length is of 8, which means that the total number of bytes in the header is 8 into 4. So that is equal to 32 bytes. So as we know, the first 20 bytes are base address, and remaining bits we call it as options. So out of 32 bytes, 20 bytes are the header, that is the base header, and remaining 12 are options. So answer is, so uh, 12 bytes of options are being carried out by this particular packet. We'll move to the third problem. Problem says in an IPv4 packet, the value of HLEN is 5, and the value of total length field is 28. So how many bytes of data are being carried out by this packet. So in this problem, the header length is given as 5 and the total length field is 28. So you can see here it is written 0x0028. The x indicate hexadecimal number. So 28 is in hexadecimal number. So in decimal, when we convert it into decimal, the total length will become 40. So 28 in hexadecimal is equal to 40 in decimal. So now we'll solve the problem. So header length is 5. So the total number of bytes in the header will be, we have to multiply it by the header value. So it is 5 into 4, or that is equal to 20 bytes. So the total length is given as 40 bytes, that is in turn 28 in hexadecimal, which means the packet is carrying 20 bytes of data. That is 40 is the total length minus 20 is the header length. So 40 minus 20, which is equal to 20. So 20 is the data that packet is carrying. Let us take up the last problem under this. Problem says an IPv4 packet has arrived with the first few hexadecimal digits as shown. So the number says 0x4500002800000100000102, so on. How many hops can this packet travel before being dropped? The data belong to which upper layer protocol? So as similar to the previous problem, the data whatever has been given is in hexadecimal format. So since you can see here is x, so which indicates is a hexadecimal address. So what we need to calculate is, one is how many hops can this packet travel before being dropped. That is, we need to calculate the time to leave. So for how many hops this can travel. Second one is which, for which particular protocol this data is belongs to. So first we'll see the uh, how many hops this can travel. So to calculate this, if we see the IPv4 datagram format, the these two fields, that is these two fields will give the information about time to leave, and the next two bits will inform the protocol, which protocol it corresponding to. So this is time to leave, that is to calculate the number of hops it can travel before it get dropped, and the next 8 bits corresponding to the protocol which is related to. So according to this problem, this 0 1 is the data corresponding to time to field. So we have skipped first 8 bit corresponding to the header length, etc. So total 16 digit in case of hexadecimal. So the next immediate next two bits, that is 0 and 1, will indicate the time to leave. So that is equal to 0 1. So this means this packet can travel only one hop or one router. So after one router, the packet has to reach the destination. If not, the packet will be dropped, or if it traveled to the any other router, then that particular datagram will be discarded by that particular router. And the second question asked here, it is the data belongs to which upper layer protocol. So the next two field, as I said, 02 is going to indicate the protocol. So as I said, the internet authority will be given, or it has given assigned a code for each of the protocol. So here it is 02. If you remember, 02 is the code corresponding to the protocol, IGMP. So the 02 is corresponding to IGMP, that is Internet Group Message Protocol. So this is the packet related to IGMP. So hope this is clear. We'll learn about fragmentation options as well as the security issues in the next coming videos. Thank you.